So, a Latin square design is an n by n array with n different symbols, and each symbol can only be seen once in a row and as well as in a column. So, the Latin square design has restricted randomization and is typically for situations where you have two extraneous sources of variation. If the columns and the rows are seen as levels of the two extraneous variables, then each treatment will only be seen once in each row and in each column. There is typically a single factor of primary interest, and it's called the treatment factor, and it has several nuisance factors. So the main advantage to Latin square designs is the fact that they can handle a case where there are several different nuisance factors, and that can't be combined into just one factor. But one of the main disadvantages is that it doesn't account for the different factors interacting with each other. It's counting on them being separate and not interacting at all, which a lot of the times is not the case. This is the standard statistical model used in Latin square design. So a lot of operations on the Latin square design will give you another Latin square design. If you permute the rows and columns and the numbers and the symbols, then you will get a new Latin square, which is an isotopic one of the first one. Now, if you select a Latin square design that has a certain number of values, you may get another design that are not equal. So this is true for p equals 5 and p equals 6. But in most cases, you randomly select or generate design by permuting the p columns and randomly permuting the last p minus 1 rows. So as an example, in a factory, there are 4 operators operating 4 machines and producing the same product. Your rows are your operators and your columns are your machines. What you're calculating is the ideal layout so that you will get the best production time. So here's an example. This is a visual for you of the example I just gave.